So today I will talk about CLIP, a model from OpenAI in the USA, and it's connecting text and images. And CLIP stands for Contrastive Language Image Pre-training. And you should, if you find this talk interesting, you should all read the paper. It's a small paper, 48 pages, where they go through the model and the implications quite thoroughly. And they also have a blog that is nice and easy to digest. But I want to start this session with a quick live demo. We will have several live demos, so we'll see if the demo gods are with us today, hopefully. So after the really first taste of the demo, of what we will end up in, I will go through image classification and CLIP, and then end up in guided image generation. And then I want you, the audience, to come with some input to see if we can do something fun there. So let's start here. So CLIP is connecting text and images, and what I will show you here is given a text, can we, like an arbitrary text of anything that you could come up with, can we generate an image from this? And here the text is a portrait painting of Stefan Löfven. So now I'm starting here. So I'm starting from a model that is called StyleGAN that is really good at generating faces. So there is a homepage that says this person does, has the address, this person does not exist. There you can see examples of where this model starts. So now it's going towards Stefan Löfven, from a portrait painting of Stefan Löfven from like regular photos of people. So I'll of course go through CLIP and explain what is going on here in the end. And so now we have trained the model, guided the model a bit here. And a fun thing here is that you can actually now generate an infinite amounts of variations of Stefan Löfven here, if you feel like it. And well, it's a bit weird, but yeah. So the demigods were with us. Here you can see the pretty Stefan Löfven, but let's go back to CLIP here. So yeah, that was the quick live demo, and then I want your input in the end. But let's start with image classification. So how image classification usually works is that you have a bunch of photos, and in order to classify those photos, you add labels to them, and the labels are numbers. So if you want to classify cats, dogs, lizards, and horses, you assign them a number or a position in a vector. So here, cats is in the first position, and the label will be a 1 for the first position and 0s for the other positions. And dog, in this case, we have decided that it's the second position, and so on. So then you take your image and you pass it through a network, and you get out a vector in the end with scores for these positions. So in this case, you get 90% match for the first index, which corresponds to a cat. So this is how we have done things up until recently, and it has been the best way of performing image classifications. And here you have a bunch of different image classification datasets. So I have a food dataset, and you have a histology dataset, and paintings, the ImageNet, which is a classic dataset, but in paintings. And you can see here that you have a classification of guacamole, even though it's a bit of a specific, special photo. But what you usually have to do is that you have to train one classifier for each of these separately. And to do that, you have to label all the photos with these numbers, right? But if you look at the labels here, besides these photos, you can see that they're actually a bit weird. So you have, on the first one, you have the label, a photo of guacamole, a type of food. So it's not regular labels here. It's actually text. So that is awesome. And this is actually not separate classifiers. It's one classifier that is applied to all of these data sets. But you can also see that it's not perfect. So the green colors here imply that the classification is correct. But you see on the medical photo here that you have orange, so it's a misclassification. But this is really starting to get interesting, right? So you have all these different kinds of texts that are used as labels. So how does this work? So it starts with text-image pairs. So nowadays you can find a lot of annotated photos online, right? So you can actually gather text-image pairs in really, really large quantities. So this photo could, for example, have the text, "My tiny kitten exploring, #cats, #pause." And that contains some more information than just the label, well, just the number 1, right? So it's a tiny kitten, and it's exploring, which kind of adds something maybe that will be associated to the background. And you have pause that co-occur with kittens. So a kitten could have pause. Yeah. So what you do in CLIP is that you collect a lot of image text pairs, and then you train two encoders, a text encoder and an image encoder, with something called contrastive learning. And that is actually quite a simple method in a sense, because you take one text image pair like this, and you say that they should be similar. And then you have a lot of other text image pairs, and you say that the image of the kitten should be dissimilar to all the other texts. So you basically just match up a lot of text image pairs and say, like, these two that we found, they should be similar, and they should not they should be dissimilar to everything else. Of course, that's not true in practice. There will be a lot of overlap, but that's fine with this method. But there is some crazy stuff going on here. So in order to get this to work, like just matching text and images, you have to, in order to get this to work as well as it does with CLIP, you have to collect a lot of data. And OpenAI collected 400 million image text pairs from the internet, from a lot of various sources. And if you think that you assume that an image is around 4 megabytes, I mean, if you take a photo with your phone, it's probably larger than 4 megabytes, right? Then 400 million images is 1,600 terabytes of data. So yeah, it's a lot. And also the contrastive learning that I talked about, it works better the more negative examples you have. So you match an image and you match a text, right? But then you say they should be similar, but then you have all these other examples that should be dissimilar. And if you're familiar with how deep learning works, you know about batch sizes, right? So usually we're happy if we have a batch size with 120 examples or something. But for CLIP, when they train this, they have a batch size of 32,000 examples in one go. So you get a lot of like information in this where you have a lot of negative examples. But in order to get this really large batch size to train on a GPU cluster, you have to do a lot of engineering work. So to get the machine learning models to be as small as possible, you use mixed precision and gradient checkpointing and half precision ADAM statistics. So like the overall theme here is quite straightforward. You have to somehow have a text encoder and an image encoder. And you produce the output of those are like a representation for a text and a representation for an image. They have to be of the same size. And then you just do a dot product and match them and say, like this pair should be similar to each other and dissimilar to everything else. But you need all of this data and you need some GPUs, right? But if you can do that, you can just collect all of the image text pairs you can find and kind of build this shared representation for images and text. And what you end up with then is a kind of a general image classification model. And you get a vision model and you get a separate language model. And of course, CLIP is transformers that we have talked about a lot in the text domain. And they were introduced in the paper Attention is All You Need. And I will not go through the details of transformers. But in the CLIP paper, they explore various architectures for the image encoding. So the text encoding is a GPT transformer, quite small one. But for the vision part, they that creates the representation for the images, they try out classical image architectures. But in the end, of course, it was a transformer that won there as well. So they use a vision transformer. And for us, that's been in language now for a little bit. We're very used to the architecture in the context of language. But it's all a bit strange how it works with images, because the normal machine learning architecture for images has historically used something called convolutions, where you scan over the whole image and you have like this overlapping patches that you look at. But when you have a visual transformer, basically you take the image and you cut it up into small pieces. And you kind of say, oh, each piece of this image is a word, and they are not overlapping. And then you just do the same thing as you do for language. You attend to all the pieces and put them through the transformer. And in the end, you get out a token that you can use as your representation or do classification with. So I urge you all to look up transformers. There's a lot of good resources online, and the illustrated transformer, the annotated transformers, and all the Hugging Face implementations. So if you want to do image classification with CLIP, how does it work? So you just write down your labels, basically. So you have a domain that you want to classify stuff into. Then you write down labels like a photo of guacamole, a type of food, a photo of ceviche, a type of food, a photo of edamame, a type of food, and so on. So basically you just use language and say, okay, this is what I'm interested in. And then you create text representations with the transformer for all of these sentences. And then when you get in an image, you compare the representation for the image to all these text representations, and you see which one gets the highest score. So, and this is called zero-shot classification. So you can see that assuming that the model is knowledgeable about a lot of various photos that you can just, I mean, you can come up with anything, right? So if you have a database like Kungliga biblioteket with old photos and you want to sort them in various ways, you can just come up with the labels of rural cottages and old city street photos and whatever. And you can then encode all your images and see what is the best matching description for this image. And that goes for basically any domain where you want to look through your data. But of course, this is only interesting if it works well. And if you look into the paper, the claim is that it works really well for a lot of varied data sets. So what you see here is a comparison between CLIP and ResNet. But I mean, these are images from the web. So there is a bias towards images that you often see on the web. So it's probably not wise to apply this straight out of the box to medical images where you're looking for a cancer or something like that. Or if you have a very specific domain, you might run into trouble. But as I mean, instead of hand labeling a lot of data and start to train a classifier from scratch, you could just try it out with some language. But one thing then is how now we're in the domain of prompt engineering. So okay, if you look at the labels here, you don't just have the word guacamole, right? So you have the sentence, a photo of guacamole, a type of food. And it's no coincidence that you have this sentence. It's because OpenAI tried out a lot of things, and they find that how you type your like your matching thing really does matter, right? So instead of hand labeling and training your classifier, you're now in the language domain where you can write different label sentences and try them out. And they show that in the paper that you can get like a 5% increase in score on a lot of these tests by just having the right language. But you can also think, if you think about this, then language contains so much signal, right? So if you only provide a model with the labels for cat and dog, it might not learn all that we want. So if you look at all the images from the web and the descriptions, you will get more information about the colors a dog might have and the environments that they are in and the actions that the dog do, and that will help the classifier to do a better job at classifying, most likely. So yeah, I mean, here we have more examples of prompts. But you can also do other interesting stuff here. So if you want to apply this to your own data, you can kind of combine the modalities. So what we see here is an example so you have the representation for the Sydney Opera House, the text, and then you get the representation for like a night. It's an arbitrary night photo, and you just combine them, you add them up, and then you search in a database and compare those to other images, you can see that you get a night photo of the Sydney Opera House. And then you have this Sydney Opera House text plus like an image of a house at sea. And you find that the best match here is the Sydney Opera House in the water. So you really have some interesting stuff going on here. This is probably not fail-safe either. This is also kind of a prompt engineering, so there are no guarantees here. But yeah. But this is also a bit weird, because what has happened with all these text image pairs is that CLIP, the model, has learned to read. And that might introduce some problems if you want to use this as a classifier, because here you can see that when you have a picture of an apple, it's correctly identified as a Granny Smith. But if you just put the little note on it with the text iPod, you can see that the classifier all of a sudden reads the text iPod and gets really, really sure that it's an iPod, which is not true. But then there has been some more work on this. So you can probably come around this a bit by having a better text, right? So you could have the text, an apple with a Granny Smith apple with a paper on it. And then it would maybe classify that higher. But still, it's so powerful that it has learned to read. So if you want to play around with this at the NLU group, we have made a multilingual and the Swedish version of CLIP. So CLIP is, in the first case, trained on English. But if you want to apply this to Swedish or other languages, you can go to Fredde Frallan Multilingual CLIP and check out our Swedish and multilingual versions. I mean, we have not retrained the networks, but we have combined networks and made them understand Swedish as well. So now on to my pet peeve here. So wouldn't it be awesome if we could just like reverse this process as well? So now what we have talked about is the original intent of the paper, which is building a really general image text matching algorithm. But what if we could use this same framework and have a text and get an image out? So if you do this naively, like for any, I mean, we have had the image classifiers for a long time, so you can imagine just doing this with the labels for cat from ImageNet. And the way I would like argue that you do this naively is that you put in a random image and you update. Instead of changing the weights in the network, you allow the weights of the image to change with the gradient. So you want it to be a dog, and you backpropagate and update the image. But naively, this doesn't work because you get these like adversarial examples, or this like adversarial. So you will get one really bright pixel that the network, if it has seen a lot of dogs, it just so happens that like this one pixel was also important for classifying dogs. So if you just let the network do its own thing, you will get like really just noisy images. But to the rescue, I'm not sure if you follow this the machine learning for some time. You have probably seen deep dreaming, like all these weird snail-like and psychedelic features. And it's a technique introduced by Google researchers, where they kind of apply some tweaks to these networks in order to get to update the images in a way that makes visual sense. So let's try that out with CLIP. So we have a text describing an image and we encode it. And then we start with so here we have the finished image, right? But then we start with the noise image and we do some magic in between, some regularizing magic, and then we put it into the encoder and compare it to the text, and we get a gradient out, and we update the image. And this magic that we do, that we can do in order to get this to work, is to, for example, cut up the image in small, tiny pieces, and then feed each piece into this image classifier. And what you get then is a lot of gradients that you can combine into the original image. But it still won't work really well. So when you get the gradient out back, you can apply some operations on it. So you can sign it so all of the gradients have the same, they're either +1 or -1, and that will eliminate like this adversarial, like really strong signal for 1 pixel. And it also turns out that this technique works much better with the visual transformer, and it's not really clear to me why, but that is the case. So if you just start with an image, you can actually combine this with CLIP, so you can get out like back propagate into the image and get the representation. But what CLIP has learned is not necessarily what we think of as interesting images, right? So it's okay if you have a dog up in the left corner, and if you have a dog up in the right corner, and it's okay that the dog is facing either way, right? So if you ask it for a dog, you will then get maybe a combination of a superposition of all the dogs that it has seen, and it's completely fine for the network. So if you want to make really pretty pictures like the one we started off with of Stefan Löfven, you can start with like a strong image prior. So you can add a generative network, and you can just jack it in. So you create this Frankenstein network, where you start with a network that has a really strong face prior here. So you can generate a face, right? And then you ask CLIP for something. You can ask CLIP for an image of Stefan Löfven, and then you just can take the face and update it, and it will be much more similar. So it turns out you can use all of these various priors, and it's, I mean, we have a lot of networks for generating images out there. So we have StyleGAN for generating faces. OpenAI came out with another autoencoder that's called DALL-E that you can use for it is good at generating photos or lifelike objects. And then there is this other paper, Taming Transformers, which is also an autoencoder that is really good at images. So if you jack these into the CLIP framework, you can have this really strong image priors, which will help with the generation and get different artistic outputs. So let's just try to generate some images. And now I'd like the audience to come up with suggestion for image prompts. So we will go through 3 of these variations if we have time, and then we'll end with the discussions. So let's try with another face prior here. So my prompt here was a portrait painting of Stefan Löfven. I mean, does anyone in the audience feel like coming up with a prompt that we can try? Otherwise, I will come up with one myself. Do you have a prompt, Magnus?
So Amaro suggests...
Or any questions?
Yeah, Amaro suggests a photo of a satanic mechanic.
Satanic mechanic. It's also rhymes, which is awesome. So let's see here. So we start with the StyleGAN prior, and we let CLIP update this. Oh, this is getting weird. He has something wrong with his forehead, I think. Yeah, so this is CLIP's idea of a satanic mechanic. Okay, so we got another one here. So the prompts for this, since we start with the face priors, it's really, I mean, anything that is related to images of humans will be nice. So here we have a photo of Bill Nye. Let's try that out as well. And you can go very deep into like how do you regularize these networks? How do you get them to talk to each other? So it's not. I haven't made the perfect version, right? You can definitely spend time on this and improve on the results that you get. But what this is a combination of CLIP and StyleGAN, and CLIP is using language to guide the network. So here is, I'm not entirely convinced by this Bill Nye photo actually, but right now we have fine-tuned StyleGAN here. I mean, it's a very quick process. Now we have an infinite amounts of shitty Bill Nye photos still that you can generate. So, okay, we get a small Norwegian lifting a colony of fire ants. That one I will save to the next network. That's not only good at faces, but I will start with portrait of the Swedish king. Here. Let's see if it works better than Bill Nye. So you have to realize also that this only knows what it has seen, right, on the internet. So among these 400 million pictures, there actually is pictures of Stefan Löfven, which I think is funny. I also tried Ebba Busch Thor, but she's not present in the data, right? So I'm not sure if Carl Gustav is present in the data either. Which Swedish king is it, actually? Is it a mix of all Swedish kings? Okay, let's just see if we can get something fun out, and then we'll try another network here. So I don't know who this is really, but it's not. So StyleGAN, I mean, generates faces of kids and women and men, and so now we're fine-tuning the whole network to look more like the Swedish king, which means that you can get all these scary. I mean, we don't usually think of him as female, right, or as a kid. So, but we can generate these pictures that has been fine-tuned towards that. But let's go on and see a photo of a successful CEO. Let's try that and then move on to the next network. Photo of a successful CEO. So we start with the regular photos, and then I don't know where this is going at all. Apparently you have hats if you're a successful CEO. And a big smile. Hats and smile. Yeah. Yeah, okay. And maybe you have a suit as well. Let's try some out here. Yeah, okay, but this looks almost normal. Yeah, you can be anyone. Okay. At least you're smiling if you're successful here. So let's move on to next notebook. Let me see if I can. So now we're moving on. The first one was StyleGAN. And now we're moving on to this autoencoder. And I will start with the prompt here: an armchair in the shape of an avocado, an armchair imitating an avocado. But then I will move on to a drawing made by a 3-year-old. So this network, the autoencoder, does not have a really good face prior, right? But it's good at making natural images. So here you can see that it's it's trying to make an armchair in the shape of an avocado here. And if you have a lot of patience and you tweak the implementation a bit, you can make much nicer pictures. But it's not for the live demo, because we don't want to wait 15 minutes to see something. So we have to do with this bit of coarser versions. But yeah, I think it's at least there is an avocado in there and with some legs. So far the demo gods has been with us. So let's try a drawing made by a 3-year-old. See where it ends up. So I have also actually cheated a bit here. So we're starting with a white picture with some gray in the middle. So that is also a kind of prior where the network can, I mean, you send in this starting points to clip, right? Yeah, so I get this potentially impressionistic childlike feeling here. The Bolivian Navy on maneuvers in the South Pacific. Okay, let's. I'm happy with these results. So let's see if we can make this really advanced prompt here. Small Norwegian lifting a colony of fire ants? Frågetecken? Question mark? I don't know if I don't know what it's implied by the question mark there, but yeah. Let's see. This I have no idea. So this is unexplored territory, just so you know. We can take responsibility for what we see, but it looks like we potentially have some fire ants here. But I don't know where this small Norwegian person is, if CLIP understands that.
I think you actually misspelled Norwegian also, so maybe
yeah, I did.
Why it doesn't.
I did, yeah. But I since I have played around with this a bit, it seems to be quite resilient to small spelling mistakes. But I don't think we would see. Yeah. Okay. So if you would let this run for some time, maybe you would get a clearer picture, but it's... So one thing that I have observed in this is that CLIP has these really good latent representations of a lot of things, but if it has not seen enough data or overlap, it kind of will make this interpolations where it just like superposition stuff. So it will just, it can't make semantically coherent combinations of concepts all the time. Sometimes it can, but otherwise sometimes it just adds like things on top of each other. Let's try wombat riding a zebra. And then I think we'll start to round up the demo session. You have some zebra stripes in here. But here we might see this superposition thing where you have some zebra stripes and you have some wombat element in the middle there. So it's not put entirely clear, I think, for CLIP, the network, what it's riding on. So it hasn't learned language fully, in a sense. We have to give it more data and more parameters. Ants. I like it. Just ants. But you can see you have the you have this in the background, this environment that's probably fitting for either a zebra or a wombat, and then you have this zebra wombat hybrid. I'll actually move on to, so this was the autoencoder, right? So now we're playing with the combining a lot of different networks. So the last thing I will show you before we move on is just dreaming straight from CLIP. So now we don't have any prior, and we will also do an infinite zoom here. So we can do an infinite zoom into ants and see what we get. So what we will do is we will ask the network to so now we just start with a noise image, and then we will ask the network to make it look like ants, and then we will enlarge the image a bit, and we will update the enlarged version of the image. And that makes so that you will continually just zoom into this image and make this kind of psychedelic voyage into the internals of CLIP. And since we're not using an image prior, these images start out a bit dark, and it also really likes to both show the visual representation, but it also likes to write out with text what so you can see that it says ants here if you can read it. So this can go on forever. Can just zoom into ants here, but I interpret this as ant-like like mandibles and stuff. So yeah, this is end of demo session. So you at least got to see a taste. Of course, you can just save these images down, let it run for some time, and you can make a video of it. Right. So that's it. You can, if you go to my Twitter, Ariel, you can see some examples of different videos and stuff if you're interested. And in summary, CLIP is really an interesting combination of text and images. It's a good general image classifier, and you can also do some fun stuff.